Hello, everybody. We're talking about conductor's view today. Um, and the first guiding principle that you should know about conductors is that electrons can move around freely within a conductor. So it doesn't cost any extra energy. You don't lose any energy for it. If you apply any sort of electric or magnetic fields, the electrons can move in response. Generally electric is what we're going to be looking at. So if you take let's say a sphere, a conducting sphere, and you place it in an electric field, so you have the electric field going across, what happens? How does it react? Well, first of all, the protons don't really move. It's only the electrons that move, because the protons are the nucleus. And so to move the protons, you have to move the whole atom. And the atom is fixed in place because it's a solid, so it doesn't really move. So when we apply this external electric field, the electrons do move, and they're going to want to travel up the field, because electrons will travel up the field because they have a negative charge. So we get some electrons along this line, along this edge of the conductor. And, not much there. And then on the other side, you are going to end up with a net positive charge, though, even though the protons don't move, because the protons don't move, but the electrons did. So the electrons were associated with these nuclei here, but because of the electric field, they have moved to the other side. So how does the electric field look then? Well, inside the conductor, the electric field is 0. It's supposed to be 2 words, but oh well. So there is no electric field inside the conductor. And the reason this is because the protons and electrons balance themselves out so that it cancels out the electric field. Because they're allowed to move around freely, they can do that. What about the external field? Well, because of the way these charges have distributed, it's going to change the external field. So it's going to come in and kind of hit like this. This one probably gets like drawn in, but doesn't quite hit. So this one should have gotten drawn into a little bit. And like this, and like this. We'll talk about why in a second. But it's going to change the external electric field because now there's charges that are going to interact with it, right? Yeah. Okay. So if we talk about potential, another big point we want to know is that conductors are equal potential surfaces. Now, to remind you guys, an equal potential really just means equal potential. It's kind of silly that we have a special word that's almost exactly like just saying the 2 words, but there you go. So every place on a conductor has the same potential. And that means that if I took one electron or a charge and moved it around, it would move around freely. Like, right? That's what we said over here. So these two are very related statements. So, but the other point we have to talk about with that is that since conductors are equipotentials, every point on their surface is the same potential. And how do electric field lines intersect equipotentials? They always intersect them at right angles, which is why I curved these the way they did. So they're always leaving the surface at a right angle, if I can draw it well. So that's supposed to be a right angle, that's supposed to be a right angle, that's supposed to be a right angle. If any of them aren't right angles, it's just because I'm a bad drawer. So I think, yeah, these are some important things to remember how these things move around. So when you guys are calculating potential inside conductors, you can treat them often like a hollow sphere or a hollow whatever. Let's put a bullet point there. Yeah. Another thing you'll find is that the charge is always on the surface. Of the conductor. So I think a final point I want to make about conductors, at least for now, is that we said how they have electric field inside the conductor is zero. They have this shielding effect. So if I took a conductor, a solid metal of some sort, sphere, and I hollow out a cavity somewhere that's not the center, and I place a charge inside that cavity, what does the electric field look like inside and outside that cavity? Well, it gets a little strange. So we can surmise that our electrons from other places in the conductor are going to be drawn to that surface, right? And you're on that surface. So even though it's like inside the conductor, you still have can still have a charge there because it's on a surface. And so because they're drawn in, we have positive charges we've left elsewhere. These probably aren't the same number. I'm just trying to get for the relative densities maybe a little. And you'll find that you probably have more positive charges on this side. Let's see, right? No, they're going to be more on... Yeah, more of them should be on this side, I think. Because they should be as far away as possible from the charge. So let's try and make more over here. As far away as possible from the other positive charge. So, but what does this do for electric field? Well, inside the conductor, the electric field is still zero, inside the metal. So this area is where the metal is. But inside here, you can still have an electric field because you're not inside. I mean, you're surrounded by the conductor, but you're not really inside of it in the same way. Like, you're not part of the metal or inside the metal. You're just in a hollow section of it. Okay, but what does the electric field look like outside? Will it be distorted so that it looks like it's centered on the charge, or will it be shaped so it looks like it's centered on the center? Well, for the sphere, actually, the electric field is going to be shaped. just like it would for any other sphere with the charge in the center. I'm drawing this terribly. You guys know what it's supposed to look like. All right. So it will appear as if the charge is in the center because of that shielding effect and the way the charge distributes itself. The conductor shields the charge. And hides its location. But because there's still a net charge, when I draw my Gaussian surface, I can tell that I have a charge enclosed and I have an electric field, but I can't tell exactly where it is. Alright, I think that's going to end this video, guys. Have a good day. See you in the next one.